what is the ferromagnetic material? What is the behavior of ferromagnetic material in the presence of external magnetic field? So this is that ferromagnetic material. This ferromagnetic material also behave as a non-magnetic material in the absence of external magnetic field, because if I bring this substance, let's say this substance, to this ferromagnetic material, they will do not attract it towards this uh, ferromagnetic material. Okay, there is no attraction. But now, if I provide the external magnet to this material, okay, now I have provided the external magnet to this ferromagnetic material. Now this is also behave as a permanent magnet in the presence of external magnetic field. Okay, in the presence of external magnetic field. So in the presence of this external magnetic field, this ferromagnetic material also behave as a permanent magnet because it now attract this material. Okay, so now this ferromagnetic material have some this ferromagnetic material have some property. Okay, so if we remove this external magnetic field, if we remove this external magnetic field, okay, I have removed it. So for a small interval of time, this material have retain their magnetic property, because again see here, if I remove this magnet, this material still will be attached to this ferromagnetic material for a small interval of time. Let's see here, I removed it. So for that small interval of time, that material still will be connect with this ferromagnetic material. So the ferromagnetic material have the ability to retain their magnetic property even if we remove the external force. So this material retain their magnetic property for a small interval of time. So due to this property of the ferromagnetic material, we use them in a transformer, in solenoid, in choke, okay, in these all circuit. Okay, inside this circuit, let's here in this here inside this coil we have this black color material. This is called the ferromagnetic material. Ferromagnetic material has the ability to retain the magnetic field even if we remove the external magnetic field. Okay, so in the presence of external magnetic field, this ferromagnetic material which is present inside this coil also behave as a magnet, and it support the external magnetic field. Okay, so now we have two substances. One is the this ferromagnetic material, and we know this is also behave as a magnet. Okay, behave as a magnet for a small interval of time. Okay, and now we have this permanent magnet. Okay, this is also behave as a permanent magnet, but this is actually a permanent magnet for a long interval of time. This is for a small interval of time. Okay, so there must be the difference in response of this material to external magnetic field. By changing the external magnetic field to this material, the response of this ferromagnetic material will be different as compared to such like material or the steel or the hard steel. Okay, so that sort of the property of this material with the external magnetic field is discussed by the hysteresis loop. Okay, so this is actually the transformer. Okay, this is the transformer, and in transformer consists of the coils. One is the primary coil, the other one is the secondary coil. The coil which is connected directly with the power supply, okay, we call that as a primary coil. This is the secondary coil. And if we provide the electric field to this material, the magnetic field will produce, and that magnetic field will interact with this ferromagnetic material. And we know that this ferromagnetic material, the molecular magnet of this ferromagnetic material, will support that external magnetic field. Okay, so now I'm going to provide the alternating current to this transformer. Okay, so this is the primary coil, and now I am going to connect that primary coil to the AC supply. Okay, I'm going to connect that to this AC supply. Now I have connected that. Okay, and this is the galvanometer, and now this galvanometer will show deflection. Okay, it is showing in its deflection. Okay, but here see the I'm going to properly connect them. Okay, here focus on the needle of the galvanometer, which is vibrating so fast, which is vibrating so fast about their mean position. Okay, which is vibrating so fast about now, which is vibrating so fast about their mean position. Okay, this is about 50 times in a second. Okay, this is vibrating because we provide the alternating current, and alternating current change its direction 50 times in a second, because in Pakistan the frequency of alternating current is 50 hertz. So here what I'm going to say is that here I provide the alternating current to this to this transformer. Okay, and here this the current changing its direction 50 times in a second, due to which the change in the electric field will produce the magnetic field in these coils, due to which the magnetic field will be present here around uh, this around this transformer. Okay, and that magnetic field will change its direction about 50 times in a second. Okay, so here the changing magnetic field interact with this ferromagnetic material. Okay, so the domain inside this ferromagnetic material will also align themselves with the external magnetic field about 50 times in a second. Okay, so there is alignment, so fast alignment of the molecular magnet with the external magnetic field. So the one important and the good property of this ferromagnetic material is that it retain its magnetic property even if we remove the external magnetic field. So when, let's say, when the current is flowing in one direction. Okay, when the current is flowing in one direction, okay, towards this magnet, the magnetic field will have some one direction, mean that this side will become north and that side will become the south. Now the current is changing its direction, so that side will become this polarity will be flipped. So here, when the polarity has flipped, this ferromagnetic material still retain their magnetic property, still retain their magnetic property. So, therefore, the magnetic field produced by this ferromagnetic material, which is called the magnetic flux density, represented by B, that is lagging behind the external magnetic field which is produced by this primary coil. Okay, so that external magnetic field is represented by H. So hysteresis loop says that H, the magnetic field produced by the primary coil, will okay will lead this B, which is which is contributed due to the domain of this ferromagnetic material. So, hysteresis loop uh, give us the detailed overview and the graphical representation of the ferromagnetic material, that the magnetic flux density, which is due to the magnetic domain of this ferromagnetic material, is always lagging behind the external magnetic field, which is produced by the change in the current of this alternating current, current, okay, this AC, and they produce the magnetic field. So this AC produce the magnetic field, which is called H, and due to that H, the B is produced inside this ferromagnetic material. That B is lagging behind the external magnetic field H. So that is called the hysteresis loop. We will discuss this in the form of presentation PowerPoint. So this was the practical explanation for the hysteresis loop. Okay, so now we are going towards the uh, PowerPoint. Now, what is magnetic hysteresis? Here, the word hysteresis means lagging behind. As we saw in the previous demonstration, that the magnetic flux density of the soft material, which is present inside the external magnetic field, was lagging behind that external magnetic field H. So, this phenomena is called magnetic hysteresis. So, let's consider a coil in the form of spring here. If we provide the current, the change in current to this coil, the magnetic field will be produced around this coil. The one side will be the north and the other side will be the south. Now, if we place the soft iron material inside this coil, that magnetic field strength will be increased, because here we know that this soft iron is made up of the tiny molecular magnets. So that tiny molecular magnets will also add it, okay, that will also support with that external magnetic field produced by this coil, due to which the strength of that magnetic field will be increased. Now, what is magnetic flux density? Magnetic flux density is the magnetism induced inside this soft magnetic material due to the external magnetic field. So the magnetic field inside this soft iron is called the magnetic flux density. So the factor which is affecting the magnetic flux density are the external magnetic field. Okay, if we increase the external magnetic field by changing the current, the magnitude of the current, then that magnetic flux will be increased. It also depend upon the nature of the material. Okay, and it also depend upon the medium between this coil and this substance. So now, on the other hand, we have the magnetic field strength. Magnetic field strength is actually that external magnetic field which is produced due to the change in the current in this coil. The relationship between this the magnetic flux density and the external magnetic field strength. Okay, here I mean that the relationship between this internal magnetic field of the soft iron and the external magnetic field is given by B is equal to mu not H. Okay, so B is the internal magnetic field, the magnetic field inside this material, okay, this soft the iron, and here H is the magnetic field produced by this coil. Okay, so this is the relation between this. Here this mu naught is the permeability of the material. Okay, and this is constant for a given
this is constant. Okay, so B is equal to mu naught H. So B is actually the magnetic field, okay, of the material. So by B is actually adding, if we provide the external magnetic field to this material, okay, it will increase that external magnetic field by contributing its own magnetic field. Okay, so here the permeability of this material will also add with the external magnetic field. So here this is that permeability of the material which is adding with the external magnetic field, and it will give us the internal magnetic field of that soft iron. Okay, now if we place that if we place this material, okay, this material in the varying electric field, mean that if we provide the alternating current to this, okay, at the first half cycle the current will flow in one direction. The one side of this soft iron will be north and the other side will be the south. Now in the second half cycle of this alternating current, that direction of magnetic field will be flip. So for one cycle, two times the direction of this magnetic field will be changed. Okay, so here in Pakistan, the uh, frequency of AC alternating current is about 50-60 hertz. Okay, it means that 120 times the change in the polarity of the magnetic field will be occur in this device which is present in the circuit. Okay, so when the change occur in the polarity, and here that is the change occur in H, the external magnetic field, here that and the magnetic field internal B will lags behind that external magnetic field. So such a behavior of the material in varying external magnetic field is given by the this graphical representation is given by the hysteresis loop. Okay, so let's consider that electromagnet, and in that electromagnet we provide the current, okay, to that coil. The current, if we increase the current here, in the alternating current, the current is changing in magnitude as well as in direction. So at first the magnitude is small and that is increasing up to the maximum amplitude. So if that is increasing, okay, so if that external magnetic field is increasing, the magnetic flux density B will also increase. Okay, that is also increase, and which is given by here this graph. So if we start from the zero, okay, so this is in the x-axis we have the H, the external magnetic field, and the y-axis we have the B, the internal magnetic field of the material. Okay, so if we increase the external magnetic field by varying the current in the coil, the magnetic field, the internal magnetic field will also increase. Okay, so in the material, there must be a time reach in which all domain of that material will align with the external magnetic field. Okay, so that is called the saturation point, and here this is show the saturation. So here in this position of the graph, by changing the magnitude of this external magnetic field, there will be no change occur in the the magnetic field of the material used inside that coil. It means that all all the molecular magnets and all the grains and domain of that material is aligned in a specific direction. Okay, here it shows this saturation point. Now as we know, there is the time reach in the alternating current it becomes zero after half cycle. So if the external so if that current becomes zero, the magnetic field in the in the coil will also become zero. So when the external magnetic field is zero, that ferromagnetic material will still retain some magnetic will still retain their magnetic property. Okay, still. So if we zero the external magnetic field, so here the external magnetic field becomes zero, still the soft iron which is present inside that coil have magnetic property, which is shown by which is shown from 0 to this b. This still here, let's say all domains are in one direction. Okay, so if we zero the external magnetic field, still here the domains are aligned in this specific direction. Okay, this is because in ferromagnetic material have the ability to retain their magnetism even if we remove the external force. So now how to again force them towards the zero? Okay, so we will apply the external magnetic field in opposite direction. Okay, so in first half cycle, that was increasing and become zero, and now in the second half cycle of the alternating current, the direction of the current will be changed, and due to which the magnetic field of that the direction of the magnetic field will also change. Now is that situation. Now if the direction of magnetic field is changed and the soft iron is still present inside that coil. Okay, so that is still present inside that coil. The opposing magnetic field will force these all domains towards its zero position. So there must be some of opposing force in the form of external magnetic field will applied on the soft material in order to bring them to its original arrangement to its original position, mean that in order to zero their internal magnetic field. So that force from here to here will be applied. This force has applied, this magnetic field is applied, and that soft iron opposite magnetic field is applied, and that soft iron, and here their magnetic field, and the magnetic field of that soft iron become zero. Okay, so that is still still the magnetic field is present in that opposing magnetic field. Okay, so here that it is present, and now the all domain of this material now is now that domains is properly aligned in the opposite direction as compared to this. Okay, and again it reach the saturation. Okay, and now if we increase the external force, external magnetic field further, the magnetic field in the opposite direction of that material will not be increased. In order to bring that again towards the zero, we will apply the external magnetic force again in opposite direction. Okay, and that will come to the zero. And now still if the that material is present in that external magnetic force, so still the molecules, the domains will be arranged in a specific direction, and here again it again it attain the saturation in that same direction. Okay, so here it seems like complex, but this is not so complex as I have discussed. If we provide the alternating current to the coil, okay, which consists of the soft iron. this phenomena will be occur in that material. Okay, so chorus, when you increase the current I, both the magnetic field, both the magnetic field and magnetic strength of the material will be increase. Okay, up to this point A. Now, if the current is turned off, the magnetic field disappear. That magnetic external magnetic field is disappear, but some magnetism stay in the material, shown from point A to point B. Now, coercive force is that opposite force, applied on that opposite magnetic field applied on that material in order to bring them to original position, mean that in order to unmagnetize them, that force is called coercive force. Now the opposite magnetization, so reverse the current, cause the material to magnetize in the opposite direction, reaching the pull magnetization in the point D. When the current is turned off again, the material keeps some magnetism in the opposite direction. Okay, so a reversal of the current again bring the magnetic field towards the 0 at point F. By increasing the current again will fully magnetize the material in that original direction. Okay, up to point A. Now, some properties derived from this hysteresis loop. So, from here to here, this region is called retentivity. Okay, so here if we zero the external magnetic field, still the material have their own magnetic property. Okay, still the material is magnetized. So this how much it has remain its magnetism, that is called retentivity, the ability of that material to retain that magnetic field even if we zero the external force is called external magnetic field is called retentivity. Okay, and that magnetic field is called the residual flux. Okay, now the coercive force is the force which force that materials again towards the again toward the zero. Okay, so the reversal magnetizing force required to bring the magnetic flux density back to zero. Reluctance is analogous to electrical resistance. This is actually the opposition of the ferromagnetic material upper to establish of the magnetic field. Okay, now the difference between the soft magnetic material. So here these are the soft magnetic material, as we mostly use the iron as a soft magnetic material. Inside this coil, these all are the soft magnetic material. So for the soft magnetic material, this hysteresis loop is very thin. Okay, mean that very small amount of the magnetic field will retain in this material if we zero the external force. Okay, and this property make them suitable for use in these devices like solenoid, transformer, and other material. Okay, in order to eliminate these residual magnetism, we will apply the coercive force, the opposite force, in order to bring them again to the zero flux. Okay, so that energy, in order to force the domains towards the zero position, that is lost, that energy has lost, that this is called the hysteresis loop. Okay, now adding how to form the soft magnetic material, we will have to add the silicon to the iron. It will create the soft magnetic material. Okay, so hysteresis loop is one of the ongoing issue is hysteresis loss is one of the ongoing issue as it prevent wasted energy. Okay, now we have the hard magnetic material. Hard magnetic material have fade magnetic hysteresis loop. It means that their retentivity, their coercivity will be more. Okay, if we remove the external magnetic field, that material will retain their magnetism up to long time. Okay, so uh, permanent magnet we use in our daily life have these fate magnetic hysteresis loop. Okay, when these material once magnetized are very difficult to demagnetize. Okay, and a substantial magnetic flux density it remain their magnetic flux density, their retentivity is more. Okay, example of this consists of the tungsten, steel, and so on. That bar magnet is actually the example of the hard magnetic material.